Hello everyone, welcome back to my YouTube channel, and today we are going to talk about how to improve large language models by using graph neural networks. It's a really simple trick, and let me show you how. So this paper right here, LLMs as zero-shot graph learners, alignment of GNN representations with LLM token embeddings. So the idea is that if we can augment graph neural networks into the LLM, it would then improve the accuracy of the language model. And let's take a look at the abstract for more information. So, in this paper, they are mainly dealing with what happens, right? What happens if the graph neural network, right? Okay, what happens if you have like a low amount of training data, right? And it becomes really hard to train accurate neural network models. So, and there's like a lot of different approaches, such as a self-supervised learning, graph prompt learning, right? But they often rely on fine-tuning with task-specific labels, which can be limiting if you want to use it in a zero-shot setting. In this case, right? So so in this paper, they introduce a framework called Token Embedding Aligned Graph Language Model, TEA-GLM. Okay, so it uses the LLMs as a cross dataset and cross-task zero-shot learners for graph machine learning. So what they do at the beginning is to pre-train a graph neural network and basically making its node representations align with the word token representations are produced by the LLM, right? Make it align, right? Then they train a linear projector layer, which is typically a multi-layer perceptron, which then transforms the graph representations into a fixed number of graph token embeddings, and using this way you don't have to fine-tune the entire language model. And now, right, and now they say a unified instruction is designed for various graph tasks at different levels, such as node classification and link prediction. So one is for nodes and the other one is for edge. So okay, and to say that these design collectively enhance their approach in the zero-shot settings, setting it apart from other methods. Okay, and they show that by using their graph token embeddings, it really does help the language model to improve its accuracy across test data sets. So, right, and that's a pretty useful thing to know, obviously, if you're gonna design language models for graph tasks. So, but for now, let us go to the conclusion, right? So that we get a better understanding overall. So, okay, right, and then talk about a lot of things here. Yeah, there isn't much new information in the conclusion, but now let's take a look at the limitations. Okay, while their approach demonstrates promise in enhancing zero-shot learning, it does have some limitations, right? But they haven't. Okay, the problem is that they have not yet explored the model's performance through specific experiments. Okay, I'm not so sure what they meant by specific experiments, but I'm pretty sure they've done some experiments like in this case here. But okay, it is what it is, right? They say it that way, then we assume it's that way for now. And I keep in mind this is a preprint, so yeah, I bet there's more work that they haven't shown yet, probably. Okay, let's go to the introduction now. Graph neural networks, okay, it is an important architecture for graph machine learning, obviously because it's able to do this message passing mechanism in order to learn the graph structure. And now let's see. Okay, right. And let's say, okay, let's use red color in this case. And to say that GNNs often have limited generalization capabilities across different datasets or downstream tasks. These limitations suggest us that we need more adaptable and universal applicable models in graph learning model. So essentially, we don't really have a base, a foundation model to work with for graph learning, right? And I bet they're going to say something like, oh, but we can use LLMs to be this general model for graph tasks. And we shall see if my prediction is correct here. Okay, to mitigate the dependency on labeled data and enhance the resilience of graph models, self-supervised learning has been adopted, such as Infomax, contrastive learning. So it's all about this mutual information maximization and contrastive learning. But obviously, they require us to fine-tune task-specific hits for downstream applications, which is consuming a lot of computational power, obviously, and it's not really applicable in many tasks, right? And also, graph problem learning enhances graph neural network generalization by using the unified task template, and they also talk about meta learning, right? And again, it's computationally expensive, and it is also not that flexible for different tasks. So since we have LLMs, right? So there have been ideas to encode LLM structures into text in order to feed into the LLM, but it's usually not great. Okay, alternatively, some people try to use the LLMs to generate the text attributes for each of the nodes in a given graph, and it works, right? But they say that it is constrained by the inherent reliance on GNNs for prediction. Exactly. So in this case, right here, you have the LM generating the text labels, the text attributes for each node. But at the end of the day, the prediction, the GNN has to take those nodes along with the text to create the prediction, rendering the LLMs kind of being this like optional component that you have, right? While you still need the GNN in this case. And they say recent efforts to use LLMs as the only predictor has potential, right? But their performance is kind of bad, and it's not transferable. Right. So to tackle this specific problem, I think they proposed TEA-GLM, right? And I already talked about this, how TEA-GLM works in general, right? And the core idea is to pre-train a graph neural network, align its representations with the embeddings from the LLM, right? And this alignment allows the GNN to use the LLM's pre-trained knowledge and allow it to generalize across different datasets and tasks without fine-tuning. That's the selling point there. If you can align it properly, then it will generalize to a lot of different tasks, right? So additionally, they train a linear projector to convert graph representations into a fixed number of token embeddings, which you can then use that, right? So that's what they say, right? But we shall see it with our own eyes soon. All right, let's quickly skim through the methods right now. So, okay. Okay, right. So they introduced TEA-GLM, right? Designed for cross dataset and cross task zero shot graph learning. It has two components, a GNN and an LLM. Right, so the GNN is used to get the node representations, and the LLM performs zero-shot tasks such as node and link classification and or prediction. Our methods involves two key stages. So there's two steps. First, enhanced self-supervised learning of GNN, where the feature-wise contrastive learning with LLMs, token embeddings is proposed. So essentially doing some kind of a contrastive learning, right, between the token embeddings from the LLMs and the node embeddings from the GNN, and see whether or not they can place the, okay, whether they can differentiate, okay, if this text is representing a certain graph, then that graph point should be close to the text point. Otherwise, it should be far away as possible, as it's not related. So that's what they're going to do, right? I guess. And the other one is trading a linear projector to map graph representations into a fixed set of graph token embeddings by designing an instruction that is suitable for various different graphs, graph tasks. Okay. Yeah, and we already seen this kind of approach in the other videos as well. So if you want to check them out, please do so. But for the purposes of this video, we're just gonna go straight to the next part right here. So okay, and it provides some kind of a definition of what the graph is in this case, but I don't think that's really important. We can skip that. And okay, yeah, we can skip that as well. Instance wise, okay, with structural information, enhance, we employ self-supervised learning for pre-training. Okay, okay, that's a lot of fluff there, but all right, let's try to understand what figure one is saying here. So it's saying, okay, okay, part one, the left part right here, contrastive learning of a graph neural network. So let's see, we have a raw graph. I don't know what RE and MF is, but it seems like, okay, so you create two different corrupted views of the graph, right? So basically, I think you remove some features, some values from the feature vector of each node, and then you create two different copies of them with two different um, uh, variations of the same thing, right? And then, okay, the next, they feed it into a fine-tunable GNN to produce some kind of a feature matrix, for instance, contrast, right? And on the other hand, they have this LLM token embeddings, of which you then reduce the dimensionality via principal component analysis, PCA, to get your principal components, and then you feed it into, and then you feed it as a part of the feature matrix, right? And then you finally get your map feature matrix for feature contrast. Okay, not so sure about what that means entirely, right? I'm not so sure, but let's move on to the next one. So the next one, we have some kind of a graph topology, probably from the archive, graph data set, right? And then we feed the graph into the GNN to get some kind of a representation, node or edge representation, which you then feed it into this linear projector to make it align with the text embeddings, right? So, and the language model is frozen, and then, okay, we give it an instruction prompt given the representation of a paper, token, with the following information, the title and the question. And we give it a set of like, okay, it's essentially like MCQ, multiple choice question in this case. Okay, so the blue box are the graph token embeddings, and this orange, no, it's not orange, right? I forgot what the name of this color is, but anyway, yep, the orange boxes are the text token embeddings. All right, and next we have zero shot tasks. Okay, yeah, so the zero shot tasks are basically, okay, node classification, cross dataset, link prediction, cross task. Okay, so that's the first figure. Just let me check how many more do we have here. Okay, okay, so it's 3 pages. Just give me 1 second. Make sure to drink water. Okay, we're back. Right, right. So, okay, right. To better extract structural information from the graph, we follow the work of some paper. So, like I say, generate 2 different views of the graph G1 and G2 for contrastive learning. So they basically do 2 kinds of perturbations to create those 2 different views. One is to remove some edges, and the other one is to mask out some of the node features, right? Oh yeah, as you can see, right? It, uh, it used to have this edge right here, but now it's removed, right? It's all part of the the perturbation process in this case. Okay, so removing edges strategy, samples, a random masking matrix, okay, such that they can just mask the entire adjacency matrix. That's understandable, right? And okay, right. And next, okay, the masking the node features strategy just samples a random mass vector and then applying it directly, multiply it with the node feature vector directly to create some zeros. All right, but they haven't tell us about the ratio of like 0 and 1s in this case, so we don't really know how much masking they're performing here in this case. What are the percentages? Okay, and then they get G1 and G2, which then they use a graph encoder to derive the node representations. Okay, which FU is the dimension of the node representation, and star represents different views. All right, I get it now. I get it now. So this is a not so clear one, but essentially what this means, these two means is that you have this something like this. You have 2 different views, two different outputs for 2 different views, essentially, but the same function regardless, right? And then you can perform that contrastive learning approach on U1 and U2. We employ a contrastive objective to distinguish the embeddings, okay, between the embeddings, right, treating UI as the anchor, while the other view UI prime forms the positive sample. Okay, so this is essentially the loss function for contrastive learning. essentially where you have the positive pair, the interview negative pairs, and the interview negative pairs. You try to reduce this in order to generate some kind of understanding in the differences of graphs. Okay, right. So the overall objective function is LINS equals to some terms, and then n more functions, and then so obviously this right here belongs to here, and there's another version right here where it's swapped in position, right? So UI, yeah, yeah. So I guess this is this essentially. They should use the same notation. Yeah, yeah. I guess UI equals to u something. Yeah, yeah. I mean, it's like this, I guess. Okay, so and they say okay, to increase the scalability of their approach for large graphs, they use subsampling approach, right? So basically, they don't do the entire thing; they just sample a few of them and do it on the samples, right? Okay, right. Okay. All right, next. How many more? Okay, just two more to go. That's fine. Okay, next. Feature-wise contrastive learning with token embeddings. Okay, so instance-wise contrastive learning relies heavily on individual instances. Okay, so they're saying that okay, the previous approach is great, but it relies too much on each individual graphs, right? Which can cause transfer issues when transferring to other datasets. And then to say there's a gap between there is a gap between the graph node representations and the representation produced by the LLMs. Obviously, one is graph and the other one is text. So how do you do that? How do you unify them, right? Okay, so and to say, okay, feature-wise contrastive loss breaks the independence between instances. For feature matrix U, again, we denote the columns in different views as this. Two terms here. Okay, so essentially they are performing another contrastive learning here, right? Okay, and the contrastive loss function is given right here. L F E A. All right. So, all right, and I say, okay, to map the node representations to the semantic space of LLMs, we use the principal components of the token embeddings of LLMs as coordinate axes, right? So this is to make sure that the representations of similar instances are closely aligned with the text embedding space. Okay, interesting. So they use PCA. Okay, let me just highlight this. Okay, right, okay. That's pretty good. Sorry guys, I'm a bit tired here, but I have to go through this paper. Otherwise, I would have enough time. Oh, dang it. Okay, so they use PCA to get P principal components denoted as this matrix here, P by FL, where FL is the size of the token embeddings. Alright. Okay, so and then they want to map the node representation obtained from the GNN using principal components. Alright, and then they do a lot more adjustments, setting the output dimension of the GNN equal to the LLM token embedding dimension. The columns of the map feature matrix denoted are fed into the loss function LFEA. Therefore, the final contrastive loss function for the entire thing is this. It's the average of the instance loss and the feature loss. Okay, and there's a remark here. The introduction of feature-wise contrastive learning with token embeddings is able to address the semantic space discrepancy between graph node representations and LLM token embeddings. Our approach enables the direct use of a graph structure and text information obtained by GNN in LLMs, thereby avoiding generalization. Okay, right. So this approach it helps to avoid the increase in test loss, right? Associated with modality alignment training during fine tuning process. Okay, okay, right. That's cool. All right. There's a few more to go. Yeah. The development of LMs have introduced, however, blah, blah, okay, okay, there's a whole bunch of fluff there. No need to read that. The instruction we design can be divided into two parts. One part provides graph information, and the other part describes the task. Here we take a side. Okay, right. So there's one for graph information, and the other one is about the task. I will assume the graph information. Okay, fine. All right. What's the graph information? Given the representation of a paper, paper set graph with the following information: title, first paper, where graph is the placeholder for graph inputs, and title is the note text information. Okay, right. And they have some justifications, right? Okay, note different from most works that uses LLM is predictor. The instruction we designed uses the title of a paper note, not including the extensive text data such as its abstract and so on, reducing the okay, right, here's a really strange one. Reducing the amount of input text not only decrease the model's performance, does not decrease the performance, but actually improves it. Right. So there's a paper that confirmed that LLMs benefit. Okay, LLMs benefit from structured information only when the target node lacks specific phrases for reasonable predictions. Therefore, using titles as a text input can help LLMs extract more critical information from graph information. Wow. Wow. This one right here. Wow. This is unexpected. This is really unexpected. I thought if we give it like the abstract, it should help, but it really doesn't. I bet the paper would have more to say about this, but we could do this some other day. But I will check it out by myself later. But this is something that we have to keep in mind as we go. Cool. Okay, task description. To achieve cross dataset capability where the model can be trained on one graph dataset and then performing reasoning on another dataset, the instruction is designed to include not only the task description itself, but also the set of alternative answers. Okay. So it also includes alternative answers. Using node classification. Okay, so the prompt is something like this. Which subcategory does this paper belong to? Please directly give me the most likely answer from these following subcategories. Okay. So include alternative answers enables the model to learn the task of reasoning the answer from a given set according to the task rather than memorizing answers for a particular data set and facilitating reasoning across data sets. Okay, right, so do that, right? All right, a bit more and we're done here. Okay, the token embeddings of the graph is crucial. We use projector to map the central node into K graph token embeddings, right? We map the representations to fixed number of token embeddings regardless of the task type. For instance, for example, node level tasks, we map the central node representation to K token embeddings. For each level task, we sum the representations of two nodes of the target edge and map this sum to K token embeddings. Okay, so essentially here, right? Here, if you have like a graph in this case, let's say graph, a pentagon graph, then what they're saying is that if you're dealing with node level tasks, right, you just get the nodes and directly feed it into the GNN, right? But for something like the edge level task where you're only concerned about the connections, right, you would need to get both into the GNN, right, at the same time, such that it would signify that, okay, there is your concern about the edge between these two nodes. Yep, so that's what it meant by that. Okay. In this way, we unify the instruction of graph tasks at different levels. Thanks to text-aligned contrastive learning, this projector is able to capture the relationship without fine-tuning the LLM, and that's pretty cool. Okay, and I have here, and I wrote something here. This approach has three advantages. When dealing with tasks at different levels, changes to the instructions are minimal, right? And secondly, fixed number of token embeddings can be seen as conditional soft prompting, right? Unlike traditional soft prompts, learning at the instance level reduces the risk of overfitting to specific data sets or tasks and make it more generalizable. And finally, okay, this work intends to include the representation of all nodes in the subgraph. We only map the representation of the central node to tokens since there's more information carried by message passing of GNN. Right. All right. And this one right here. Okay. To ensure everything is compatible and facilitate comparisons, right, we map the node features into a consistent vector space. So they use a BERT model to encode the raw text, generated raw text associated with each node and generate the node features. Okay, right. So basically, converting the text into vectors, like a sentence word would do. And you can find this on Hugging Face if you want to use it. Okay, so and let's say, okay, we pre-train the graph model using contrastive learning with the loss function, right? And after that, the parameters are fixed and they use the pre-trained model to obtain node representations, right? And then they train a linear projector on specific tasks within the same data set. Okay. There. Okay. And finally, they validate the performance, the accuracy of their model on unseen tests, on unseen data, right? So, okay, so in this test, they use GraphSage as their GNN and Vicuna as their LLM. Okay. So right here, okay, so there's experimental results, but we're just gonna go through it briefly. But before I start reading, let me take another sip because I'm getting quite sleepy already. H2O is my coffee. Okay, anyway, let's move on. Um, all right, table one, zero-shot accuracy on citation and e-commerce datasets. Well, highlights the best results and so on. And what you know. Well, okay. Well, it won everything. Uh, it even outperformed GNNs, right? Uh, let me see. Somehow the LLMs, right? The LLMs, even with like chain of thought, uh, it's kind of weird though. Chain of thought gave like 50% accuracy, while not using it already gives like 70% worth of accuracy. Kind of weird. Okay, right, but that's graph GPT. Okay, so they use graph. Sorry. They use Vicuna 7B. What's the okay? And then they use Graph Sage. Got it. So Graph Sage is around 30% accuracy. Yeah. Okay. Yeah. So their approach really works that well. Okay. I'll take note of that. Well, the other one. Okay, right here. The area under curve is also pretty good, indicating high accuracy among other approaches, right? Yeah, it works pretty good. Okay, how about this one right here? So it's unseen data sets. Oh, as for unseen tasks, right, if you remove any component, the accuracy immediately drops by a lot, especially for the link prediction right here. But for node classification, it doesn't really drop that much. If you remove any of these FC and GT components from it. Interesting. So, okay. All right. Right. Okay. Huh. So this is some related works. Yeah. So overall, the paper has some really great results, right? And I think all of us have learned something here. Is that if you want LLMs to perform well for graph data problems, then you might want to take a look into graph neural networks and then see how you can incorporate it directly into LLMs. And with this approach, it's really simple. You don't even have to fine tune the entire LLM in order to do so. Yeah. So yeah, I think that's about it really. So if you like this video, make sure to like, comment, and subscribe, and I will see you guys in the next video. Bye.